Hello, in this video we're going to be talking about related rates, which is a type of word problem that we come across in calculus. One of the major things that we need with this is implicit differentiation. We are going to see equations like this and make them, and then use implicit differentiation to find the derivative with respect to neither of the variables that are there in order to create this new equation. We'll know some of these rates, but not others. Here's an example of a related rates problem. And what I've done is I've written out the different steps that we're going to take through this one. This one's a little bit of a simpler one, but that really demonstrates the different steps that you need to take. So we have a circular plate is heated on an oven. It increases at a rate of, we've got one right here, and we want to figure out the rate that the area is increasing. This is where that related rates idea comes from, is we have a rate of radius increasing, and we also have an rate of area increasing, and we want to know what the relationship between those rates are. So we start by identifying what are our variables. Well, we've got a radius of our plate that's going to be changing as this heating is happening, and the area of the plate is also going to be changing. So we've got two things that are going to be changing. Then we want to draw a picture. It's a really simple step, but it really helps us see what's going on with this problem. So we've got this circular plate of metal, and its radius is increasing. So that's what this red arrow is. That heat is causing it to increase. And it's got that rate of 0.1 centimeters per second. So I know that the change in the radius is changing every second. So change in radius versus change in time. We want to know what's going on when the radius is 50 centimeters, so I'm also putting my 50 centimeters in there. Next, we want to say, okay, what is the rate that we're seeking? So that's this thing that we're trying to find out. What is this rate? The plate's area is increasing with respect to time. So as the area increases every second, just like we know that the radius is increasing every second, how much is the area increasing every second? So then we want to write an equation with number one's variables. So we know stuff about radius and we know stuff about area. And so what's the relationship in a circle? Well, we might remember that the area of a circle is pi r squared. So let's use that pi r squared equation because that's got radius and it's got area. Next, we differentiate this thing with implicit differentiation with respect to time t. Note that neither of these variables are t. So we are going to find the derivative of this with respect to t, creating a dA over dt using implicit differentiation. And then the derivative of this is also going to require implicit differentiation. So we get this dr over dt. I'm excited about that because we know what dr over dt is. It's this 0.1 decimal number over here. Next, we're going to substitute in our variables. So we know that this dr over dt is 0.01, and we know that our radius is 50. Let me get out of the way here. And we can just plug all of those things in, and then just a matter of simplification, we get that dA over dt being pi. So now we know what dA over dt is, the thing we were looking for. It is pi. Now we need to interpret this in what it means in context of this problem. So this is what's going on with our area. So at the moment in question, you could also say when the radius is 50 centimeters, the area of the plate is increasing at a rate of pi centimeters per second, centimeters squared per second. I know it's increasing because this value that I found here is positive, and I know it's going to be centimeters squared because I'm talking about area, and area is like centimeters squared as opposed to this radius, which is a distance, and that would just be centimeters. So this would be the final answer to my question. In summary, for this page, we find a variable, draw a picture, figure out what we want, write an equation, differentiate implicitly, then substitute. Make sure you do the substitute after you differentiate, and then finally interpret the value that we get. In this example, this airplane is flying over this radio center, and so we're trying to figure out stuff about the speed of the airplane. So there's different things that are happening. The plane is getting farther away from the radio spot, and it is also moving forward. So there are two different distances that are changing. Next, we want to draw a picture. This is out of the Finney textbook, and they already drew a picture for me, so really I just have to fill in those bits. So we have an altitude of 7 miles. Now that's going to stay constant. There's nothing about this saying that the plane is moving up and down. So that is one variable that will stay constant. And I didn't add it to my list in number 1 because that's constant. Next, we have the plane is 10 miles from the antenna. So that is talking about this S value. And the problem even told us that, hey, S is 10. And then the radar detects the distance. S is changing at a rate of 300 miles per hour. So that is the change in that S value. So that would be our D change in S as time is changing is going to be that 300 value. Now, this is just a little right triangle, so we can also figure out what that X value is using the Pythagorean theorem. Am I going to need that? I don't know. I'm just trying to fill in this diagram with as much information as I can. There's nothing else about this problem that I've been given. Next, we need to interpret what are we seeking. So there's this final question. What is the speed of the airplane at that moment? So we need to figure out what is the change in that X value, because that is the speed of our airplane over change in time, because that'll give us miles per hour or per second. Miles per hour, because that's based on what ds is over dt. This is miles per hour. So dx over dt will also return miles per hour. Next, we want to write our equation. So just like I did before, I'm going to use the fact that that is a right triangle and use the Pythagorean theorem. However, this time, I'm not going to substitute in that value of s because I want to keep that a variable. If I put in a 10, that's locking the distance between the radar dish and the airplane, and I want that airplane to keep moving. Now I want to differentiate this thing with respect to time t because I want to know what's happening to those distances as time is changing. And neither of those variables is time, so I'm differentiating with respect to t. The derivative of 49 with respect to t is just 0, so I'm not going to write it. Then we get a 2x dx over dt, which I'm excited about because, hey, that's the thing I'm trying to find. And that's going to equal the derivative of s squared will be 2s ds over dt. Now it's just a matter of substituting in the information that we have from our diagram, hoping that we can solve for dx over dt. If we're not able to, we'll see if we can poke around in the diagram to get some additional information. At this point, it's just a matter of simplification. So we got to do 2 times 10 times 300 divided by 2 square roots of 51 so that we can get our answer. I'm not going to eat up video time typing that in. I got 420, some decimal stuff. So all that is left is now to interpret what that means in context of my problem. Let me type that up. When the airplane is 10 miles from the radar, it is traveling at 420.084 miles per hour. Done. Thus is the end of our video on related rates. Keep in mind these 7 steps in order to work through a related rates problem. First, identify what variables you have. Take the time to draw a picture. It really helps organize that information in a way that you can easily tell what's going on and interpret what's happening. Decide what is the rate that you are seeking. What are you trying to find? And then write an equation that you can implicitly differentiate with respect to time t. Finally, substitute your variables. Make sure you do that after you do the derivative. If you do it at the beginning, it locks all of our rates. So we want things to still be moving. So do that after you differentiate. And then finally, write a sentence to interpret what's going on with your problem. Thanks for watching this related rates problems. Hopefully they don't give you too many problems. Hey, bye-bye.